Okay, we have already got the distribution of our estimate of the slope, and now we're interested in get this confidence interval for the slope and confidence interval for the line, for the regression line, and prediction interval for a single predicted value. Okay, let's start with this confidence interval for the slope. So we use the same procedure. Oh, well, sorry, I forgot to put it to slideshow. We will use the same procedure for finding confidence intervals that you used in basic statistical course. If you took this stat 5301, which is great, or any other like fundamental statistical inference class, you will know these techniques. We find that, let's just treat this alpha being 0.05. So let's just say this is a 95% confidence interval. For example, if alpha being 0.05, this interval for the slope would be something like this. So the estimate of the slope plus or minus, this is the a t statistic that you will calculate. Well, we showed this t, what this t looks like, and normally you would have to look up the table and to find this value by specifying its degree of freedom and what is the confidence level, your the significance level or confidence level you want to get to in order to get this t value. And then this t value times the standard error of the estimated slope. This is how you get the confidence interval. And I said this t is this quantile of the t distribution with n-2 degree freedoms. Well, I think the best way is just to show you an example. How do you really calculate this interval with this formula? And I will specify how to find each of this quantity. Still, we're going to use the election example we have, and we know there are 50 states in that data set. So n is the data size being 50. We need this n because n-2, right, is the degree freedom. So this is n-2 being 48. We get the estimate of the slope from the output here. This corresponding to the slope estimates is this. And the standard error, you just define it here. The standard error of the estimated slope, 0.03363. And this t value is the tricky one, right? How do you find this? If you still remember, we can get the distribution value in, well, you can get it by looking at the table, but in this course, we are going to use R, and we can simply use this function. Qt is the quantile of t distribution. This is the, for the quantile, this is specifically for alpha being 0.05. So that's a 95% confidence interval. So this is the for the quantile, and this is the degree of freedom. And just by typing into this thing in R, you will get 2.01. So this is your t value for the confidence interval calculation. Just plug in every single element, this beta 1 hat, this t value, and the standard error of the estimated slope. Well, we get this interval being 0.99 and 1.12. Well, hopefully this is clear on how to calculate the confidence interval for the estimated slope. Okay, now we will talk about the confidence interval for the regression line. but we want to find this interval for the unknown population regression line at x star, a specific given value for x. So the population regression line at x star is like, we know the regression line is the expectation of y given x. Now we given x and at x star, so this is just beta 0 plus beta 1 times x star. And then so again, let's use alpha being 0.05. So this the 95% confidence interval for it is like this. So again, this y hat star is just this. I think I'd better just put this y hat star equal here so that it's clear to you that this is what it is. And this y hat star plus or minus this t value, again, you can get it with r and times the standard error. Now this time the standard error is different from before, right? The standard error in our previous slides, this is standard error for beta 1 hat because we are looking for the confidence interval for beta 1, right? But here we're looking for the confidence interval for y, for the regression line for y. So this is different from previously because we're working on different things, but the whole structure of how to get a confidence interval is the same. It's just the estimate plus or minus this t value times the standard error of the estimates. Well, to put this simple, you can just use this R command to find the confidence interval for the model by use this predict.lm, and this argument is your linear model object, where in the election example we have my.lm being this my lm object here, and you specify the interval you want is confidence interval, so you have to tell it interval equals confidence. And this is how you get the confidence interval for the regression line. So next, we want to get the prediction for predicted value y hat. So we want to find a prediction for y at x star. Oh, sorry. Did I say y hat? I mean y star. We want to find a prediction for y at x star. So that's what we call y star. And again, this x star is a specific given value for x. And this is a random variable y star, and we want to find the prediction interval for this y star. Well, in principle, this prediction interval are wider than the confidence interval of the regression line because we are accounting for both the uncertainty in the estimate of the line. So we're estimating the line, and also for the single data y star, we also have the variance there. So we have incorporated both uncertainties into this one interval. So that's why it's wider. We have more uncertainty incorporated. So in practice, when you're trying to calculate this prediction interval, you can just use this argument. You do prediction.lm. So again, this is your LM object, where in our election example, I call it my.lm. And you specify the new data. You can put it into a data frame. So the variable name, if you call it x, equal to a vector of data. So you have a whole vector of data to predict. You just specify what the new x value is, and that will give you the prediction interval for that for the corresponding y star. And you specify the interval being prediction interval. So that will give you prediction interval. Yeah, this is the main point, comparing this confidence interval and prediction interval for this Y star, is that you have two parties of uncertainty incorporated. That makes the prediction interval wider than confidence interval. And well, sorry. And I did calculated used our example, election example. So this is the confidence interval. You see here, I specified confidence. You get the confidence for the first five data points. So this is your predicted value or fitted value. And this is the lower bound of the intervals. And this is the upper bound of the intervals. And on the right-hand side, we have a prediction interval for the data we have. If you notice that I didn't specify what the new data is, as seeing here what our new data for the prediction, it's when I ignored that argument, that means I'll do prediction on the data, on the original, on the X we have. Yeah, that's it. I didn't give it new data to predict on. It will just predict it based on whatever X value we have. So again, the lower bound and upper bound. If you do the comparison between these two, confidence interval and prediction interval, you see this one is narrower, right? Because 33 is greater than 30, and this 39 is greater than 35. So this one, this bound is definitely wider comparing to this one. And if you go through all the following, it has the same pattern. Okay, here's a small illustration. Like when I calculate the confidence interval for a new predicted Y, see, I have this X, I have this Xi, and I'll do a prediction on this, for this given Xi. The predicted value will be at our regression line, right? This would be my Y hat for this given Xi. I mean here, but if the data is somewhere here, I mean the true data, we have our predicted data being at the regression line, but if the true data could be here or could be upper, so it has some variability or some uncertainty on this prediction. And when we do the prediction interval, so we would have to account both where this line would be located. So this is the uncertainty from the regression line. And we have to add up the variability, the uncertainty from this single value. So the true value can be higher or can be lower or further or closer from this regression line. So that would make the prediction have one more layer of uncertainty. So this is just to intuitively show you the in this picture, to show you this prediction interval are normally wider than confidence interval. So this dark blue line lines are for the confidence interval along the regression line, and the prediction interval for like single given new X values. Well, okay, so this is the intervals for the inference part. So now you can tell, without knowing the distribution of this beta, we won't be able to do all these inferences. Like including previous hypothesis testing, it's based on a t-distribution, and here again we use this t value. That means we are based on t-distribution. So again, we started with those assumptions so that we can establish the distribution of the of the slope of the data so that we can do all the following things: hypothesis testing, confidence interval, prediction intervals, etc. So this is the logic. This is why and how we could do the inferences. All right.